Name other human sources of atmospheric CO2. And we've talked about many of them, like cement production, driving our cars, manufacturing. I asked this class, what is the decomposition product of methane in the air? And all of you knew the answer. Right. That's fantastic. And we've talked about adsorption already. For example, zeolites, silicas, charcoals, metal organic frameworks are all characteristic materials for adsorption. So, now that we were talking about adsorption, we talked about isotherms last time. Remember, we talked about the Langmuir isotherm after Irving Langmuir, and that at low pressures, the amount absorbed relative to the pressure is linear. And that became a pseudo-Henry's law, yeah, for this particular system. So now we want to ask, what about operating an adsorption column? How does this work practically, and what do we need to do? So we understand that flue gas with carbon dioxide comes in, and something like pure nitrogen leaves. We need a purge gas and capture that CO2. So the question is, how do you do that? Many of you have made indications that you know already. One is to increase the temperature of the bed and desorb the gas. And another would be to decrease the pressure. This is called temperature swing adsorption, and this is called pressure swing adsorption. These are useful approaches for how to do this. So let's first talk about temperature swing adsorption, especially in the context of these linear regimes for Henry's law. So if I plot the amount of CO2 on the surface as a function of the pressure of CO2, I have a line, a straight line, that's Henry's law for this system, let's say at temperature 40 degrees C. The flue gas comes out of the smokestack of my industry at 14% CO2, typical for a coal-fired power plant. And that means that the pressure of CO2 is at 0.1 atmosphere. So it's at this point on the line in terms of the amount absorbed on the surface. I raise the temperature. The effect on the Henry's law constant is to change the slope of the line and make it flatter. Yes? And so now if I look at the temperature, the pressure at which I need to desorb CO2, I desorb it into the atmosphere, or actually I desorb it into the compressor, where I'll make supercritical CO2, and that is 1 atmosphere. So there's the starting point, there's the ending point. And if I look at the difference of those, this is the amount on the surface at 40 C and the amount on the surface at the final temperature. And the difference between these two numbers is the working capacity of the adsorption bed. And it makes a lot of sense to you, I hope, that you want this number to be as large as possible, so that for each cycle you get the most CO2 on and recover it. And so a question you could ask yourselves is, what will the working capacity do if I increase this temperature? That is, if I make it flatter. Okay? And I'll let you think about that. The question you could put in your notes to answer with your friends over tea later. Well, what about pressure swing adsorption? And here we have flue gas coming in and then a sweep gas coming out that could be at lower pressure. So again, we'll go to our diagram in which we have the amount absorbed as a function of the partial pressure. Here's Henry's law for the adsorption bed at 40 degrees C. And as I said before, 14% CO2. That's at this point on the curve. And now what we're going to do is drop the pressure from, let's say, this pressure to this particular one. And you see there, we've moved along the Henry's law line, and so the working capacity is the difference in those two numbers. And the same principle applies here. I want the biggest change in these two numbers, the most working capacity for each pressure cycle. So if I have a very small change in pressure, I have a very low working capacity. If I have a very large change in pressure, I have a very high working capacity. But large changes in pressure mean I need big pumps to reduce the pressure. And so there's a trade-off there between the operating costs and the capital costs to make this happen. And a question you might want to ask yourself is, will this working capacity, the difference between these two numbers, increase or decrease as we move up and down this line? And I think I sort of gave the answer away on that question. So how do we optimize this working capacity? What we need to do is, again, trade off in temperature swing absorption. Where do you get the increase in temperature? You take steam from the power plant to increase the temperature of the bed to desorb. In the case of pressure swing absorption, you're using electricity to run pumps. And that's the trade-off between these two. And recall that we talked about earlier on in the slides, calculating the parasitic energy so that I can compare these two processes. Remember, the parasitic energy contained terms having to do with the work, with the heat extracted from the power plant, and also the electricity extracted from the power plant. So one last attribute of the absorption column that's important for you to understand, and that's the breakthrough curve. What does a breakthrough curve look like, and what do I mean? So how well do we know? Here's a cartoon of a tube that's packed with a powder, silica, charcoal, zeolites, metal organic frameworks, etc. It's a packed bed of powder. And how well do I know that all the material is being absorbed, all the gas being absorbed as I pump it through? So let's just pick a tube, and I'll arbitrarily take a point in space down the tube of distance L, and I'm going to put a detector here. And that detector will measure the pressure of CO2 over the inlet pressure as a function of time. At a slice, I'm looking at CO2 as a function of time. And what do I expect to happen? Well, at time t equals 0, I put the CO2 in, and it marches through the bed in a nice straight line. And here's length L. Boom, it hits that position. It jumps up, and that's what I see here. There's the process there, a step function. And what do we see when we add the adsorbent now? So we're going to see a different arrangement, but it should still be a step function. Here, for example, is the partial pressure of nitrogen. Nitrogen doesn't adsorb. It passes through just as though there was no powder, with the exception of a little factor having to do with the void volume of the nitrogen. On the other hand, if I look at carbon dioxide, because the bed is adsorbing the carbon dioxide, there's going to be a delay compared to nitrogen. That is, during this window of time here, the packed bed is absorbing CO2 and it's not absorbing nitrogen. And so there's a lag there. So measuring breakthrough curves is a way for us to assess how well the bed is performing when we do the adsorption process. So here's another cartoon. How will CO2 propagate at time t equals 0? Here's the concentration in the bed at the distance L, some point right here. At time t equals 0, there's no CO2. After some period of time, no CO2. And then suddenly the CO2 appears. That's because this part of the bed has now been saturated with CO2. There's no more left to adsorb. We've reached the limit on the Henry law, and so now we see CO2. So this is what I mean about breakthrough. You're at a position L, you see nothing, 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 boom. There's the CO2 coming through. That's the breakthrough. And of course, that's the time when you stop the bed and you take it and do the desorption to get the CO2 off. So calculating these breakthrough times turns out to be of considerable importance in designing adsorption columns. Now, what happens when we, say, do a temperature swing? So let's run backwards now. I'm still at position L in the bed, and now the sweep gas is going to come back the other way. It's at higher temperature, and CO2 will desorb. So at time t equals 0, I still have CO2 in the bed, and then the CO2 moves back to 0 because I'm desorbing the CO2. So there's none here, none here, none here, because I'm desorbing the CO2 as that progresses through. So a breakthrough curve can be seen both in adsorption and backwards in desorption. Of course, you know that people know how to calculate these things. I've decided not to walk you through the mathematics again because it's in one of those videos. It's actually the same physics. That is, I take a little slice in space and I do a differential analysis of mass conservation in this slice of space. So that is the accumulation of CO2 input minus output. And then I can solve those differential equations to get the density of CO2 as a function of time in the reactor. Once I've done that, then I can look at various process variables to see how they adjust the breakthrough curve. So I've done those calculations myself with the solving the equations, and I've calculated the concentration as a function of time. And now what I'm going to do is move this slide bar, which will change the void fraction of the bed. That is how much powder versus how much open space. So if I've done this right, you'll be able to see how the curve changes shape as the void fraction goes from a small number to a big number. How about if I change the Henry constant? So if I move it, you see the breakthrough curve moves both in time and its profile changes. It gets steep or not. Steep curve is a good one. A flat curve is a bad one because that means you don't get clean separations. How about the dispersity? That is to say, what happens if rather than having the front move through the bed uniformly, say at the edges it goes faster than the center, as you might expect. And again, I can do the same thing and recognize what happens is I'm flattening or sharpening the breakthrough curve. So here are some breakthrough curves that I just snatched from the literature for you to see that people are publishing. Here's a paper in Science last year in which the authors were comparing this material, all these different materials. This is the breakthrough curve. There's the concentration of CO2, or in these curves, nitrogen and oxygen, as a function of time. And notice that the beds don't absorb nitrogen or oxygen at all. That's why these curves are flat for nitrogen and oxygen, or maybe just a little bit. That's good, because we want those gases to pass through. And you notice from 0 to about what this is, 200 seconds, the sodium X zeolite is absorbing all the CO2, and then there's the beginning of the breakthrough curve. And if you look at these various materials, you'll recognize, gee, this particular powder has the most capacity to absorb CO2 because the time for breakthrough to occur happens to the latest. So this is how you will see in the literature a lot of adsorption processes characterized, not in terms of Henry's law, but in terms of breakthrough curves. They're relatively easy to measure. You have a pipe, you pack it with powder, you have the inlet gas at one end, and at some position you have a detector. CO2 is easy to detect with infrared, and so these things are relatively straightforward to accomplish. Yes? Yes, please. Yes. So the answer is material selection, okay? But I'm going to cover that explicitly right now. So let me just say, okay? You're a chemist and you're building this solid and you want it to selectively hold on to CO2 but not nitrogen or oxygen. So you could try and do it by size, CO2 and nitrogen, but it turns out CO2 and nitrogen aren't that different in size. It's actually very hard to do. So what you have to do is you have to build your solid that has molecular components that are attractive to CO2 but not to nitrogen or oxygen. An easy way to do this, and this is the section I'm skipping, but it should hopefully be obvious to you. We talked about absorption yesterday. We talked about using amines because they react to form these carbamates. So why not take a solid and attach to the solid a little amine functional group? So the CO2 comes through and it makes the carbamate. It does in the solid exactly what happens in the liquid, but you don't have water. So you don't have to worry about moving water around. So when you desorb and reverse the reaction, go from carbamate back to the amine, you're not boiling a lot of water. And so this is one of the big advantages of adsorption as a process for doing carbon capture, is that it turns out to use much less energy than the amine processes. But there are many issues now with material selection. So this is my particular area of research, which I'm not really talking about much, but this is what I'm most involved in. And I should probably tell you there are many challenges to attaching amines to materials or designing their chemical functionality so that they're more attractive to CO2 than nitrogen, but not too attractive, because then you need too much heat to get it back off again. There's a very large community of people working on this, and it would be, in my opinion, the answer to carbon capture were it not for membranes. That's where we're going next, okay? So in terms of how effective are these strategies? Absorption, easiest to buy, worst to run. Adsorption, the subject of a lot of research, not yet in place. Membranes, take a look. So what do I mean by membrane separations? So now we're going to look at a thin film of a material in which the flue gas is on one side and downstream is pure CO2 or nearly pure CO2. So let's talk about membranes for carbon capture. I really need to understand the mechanism by which this happens. I need to measure the selectivity of this thin film to pass one versus the other. As Professor Bhatti has been talking to us about, understanding mass transfer and diffusion reveals that there are limitations to how far these can go. But it turns out that process engineering is the most important thing. So I'm going to spend our time today on membranes, really talking as much as I can about process engineering because it's a huge surprise. So some years ago, when carbon capture first became of interest to the United States Department of Energy, they were funding research into using membranes. They reached the conclusion that it will never work. And they stopped funding the research. Process engineering came along and made enormous contributions, which I'll detail. And now the U.S. Department of Energy is funding research. And now membranes are in pilot plants at coal-fired power plants, and they're performing very well. We'll get to that. So what is a membrane supposed to do? It separates blue balls from red balls, just like we talked about with Mr. Boltzmann. And the flow through this membrane requires a driving force. That is, on one side, you have to have a higher pressure than the other side. Although it turns out, to really appreciate the subtleties, it's really the chemical potential is the driving force. And there are a few people in this room, I know, who understand the difference between this phenomenology, a delta P, versus a deeper thermodynamic understanding of a gradient and chemical potential. It turns out delta P is an approximation for the chemical potential as a driving force. Membranes are used widely already, particularly in the area of reverse osmosis, which is to say you can apply pressure to salt water and the ions are excluded and the fresh water goes through, and you can generate fresh water. In fact, in California, as you probably know, there's a considerable concern about drought. And here's a very large desalination plant on the beach of Southern California, and they run this particular process, which uses membranes. These membranes are very elaborate in their construction. You don't need to look at the details just to recognize that these are highly engineered materials. And they have elaborate physical chemistry associated with how ions, particularly in desalination, move through pores relative to how water molecules, which are not charged, move through the pores. If you're a student in my department at UC Berkeley, you have a laboratory in which you are doing air separation membranes. These cylinders here are packed with these membrane materials. Air comes in one end, and pure nitrogen or nearly pure nitrogen comes out the other end. And the biggest use for these membranes commercially is, anybody know? These particular membranes are used to make nitrogen to inflate the bags of salad that you buy in the grocery store. So do they sell those in the grocery stores here? You buy a salad that's sort of pre-made in a bag. So that's not air in that bag, it's nitrogen. And they're the food industry is the biggest user of nitrogen. Interesting. Yeah. These membranes are very elaborate in their construction. Here's a in silico calculation of what one of these membranes looks like, but here's a micrograph. This is the active membrane material right here, and this is the material serving as the mechanical support. So these are very, very thin films in order to allow the best flux of ions through. These particular materials are made of polymers, and that's certainly one of the materials of choice in many of these separation processes. Here's another example of, again, a simulation, and again, micrographs which show the packing of these solid materials, such as metal organic frameworks, on a mechanical support alumina, so that you have the pressure on this end. CO2 is making its way through this end, but not nitrogen. Zeolites and moths again. So what does a simple membrane separation look like? What do you think is going to happen, or what determines how these molecules move through? It turns out this has been an area of study for some decades, and it's very, very subtle. Right? So one thing that would cause CO2 to pass through a membrane more easily than CO2, because if you look at these molecules, as I was saying earlier, they're actually not all that different in shape and size. They're both cylinders. One's a little longer than the other. They have different molecular weight. So anything that depends on mass would be a good separation scheme. The kinetic diameter is not so different. That's going to be very difficult. And of course, the chemistry would determine. So again, if you want to do a good separation, you would imagine a membrane in which, for example, you had an amine group. And there you take advantage of the chemistry. So one way to do membrane separations is called molecular sieving, in which the channels in the membrane fit one molecule but not the other. It doesn't work so well for CO2 and nitrogen because they're very similar in not length but diameter, if you think of them as a cylinder. So you might ask yourself what factors would influence the selectivity, and it's just the spacing relative to the size of the molecules. But as you can imagine, the driving force pressure-wise to move molecules through would be pretty extreme. Knudsen diffusion is another mechanism by which this can happen. Knudsen diffusion is a specific name, and it implies that a gas moves from one place to another by bouncing along the walls. So it's very low pressure. And so a Knudsen diffusion, what happens is the heavier masses move differently than the lighter masses, and you achieve a separation in that particular way. This may be a delicate subject for you, but Knudsen diffusion is the mechanism by which uranium is enriched to make a nuclear bomb. Uranium hexafluoride is a gas, and you have it go through these membranes, and the membranes are aided by centrifuges so that the force of the molecules going through is higher. And of course, the infamous incident in which the United States disabled the Iranian centrifuges for production of their own nuclear weapons. You're all aware of this in the news? Yeah? Yes or no? No? That's one of those things. Okay. Knudsen diffusion works for separating things on the basis of mass. And that's what I meant there. The most important mechanism and what drives water desalination as well as CO2 separation is called the solution diffusion mechanism, which is to say you have a solid material in which two things happen. These species have to dissolve in the material, even though it's a solid, and then they have to move through the material. That is, they diffuse and they're dissolved into them. And the factors that affect the selectivity are a little more subtle. We'll come back in more details in later. There's one other mechanism that's commonly found. I've sort of alluded to it already. It's called facilitated transport. It's where you imagine a structured material where, for example, CO2 and water react with an amine on the membrane, and a neighboring amine undergoes this shuttling reaction, and you wind up sort of carrying CO2 membrane on the basis of these sequential chemical reactions. It's surprising that you would imagine that would work very well, but it turns out this is the mechanism by which hemoglobin transports oxygen in your lungs. So this facilitated transport is very effective, especially in comparison to just diffusing through the membrane. So you'll find some people in the literature, this particular reference here, in which they're trying to craft polymeric materials in which they introduce these amine groups so as to engage in this facilitated transport. So let's look at some of the engineering of these particular membranes, and let's get familiar with some of the language that is used in membrane science. The feed gas, the retentate, and then the permeate. The permeate is the gas that you want to recover. That's the one that's rich in CO2 that you'll compress and pump underground. Let's just imagine we're going to draw a slice in space through this membrane, and again we're going to conduct one of these analyses of concentration profiles that includes fluxes, and we're going to ask what contributes to the transport of CO2 in this material. So again, I made a slice through the membrane, and now I want to ask what is the concentration as a function of distance as I go through the membrane. So here's the feed concentration of CO2, 14%. As it approaches the membrane, ideally, it's flat, but of course, there's a not quite ideal mixing, and so the concentration is a little lower on this side of the membrane. Something happens in the membrane, and on the other side of the membrane, I have less material, and again, I have this little drop-off here because it's not perfectly well mixed. So inside of this material, I have a much higher concentration. And why is that so? How are these concentrations related? So one would be that this is the solubility. This difference right here is the solubility of CO2 in the membrane. If it's more soluble in the membrane than the gas, then this number is higher. And if it's less soluble, it's lower. So now you see already that calculating or understanding the solubility of CO2 in your material is very important. So what about the flux through the membrane? That gets you how much CO2 is in there. So you have a driving force, that's a pressure gradient, and then, of course, the membrane material properties and the gas properties are important. But the flux represents a driving force times a coefficient. This goes back to that video we showed, in which all things in chemical engineering are rate equals a famous number times a driving force. And this is certainly true here. It's Fick's law that determines this. Here's a position in space. Here's a neighboring position that's differentially different. And if we have a concentration gradient, there'll be a flow of molecules through. Mr. Fick figured this out long, 100 years ago, that the flux is given by a diffusion coefficient times a gradient. And the flux is in units of per unit area as you go through these membranes. So how do we relate what we measure to the material properties? So here is the gas coming in. It dissolves at a higher concentration in the membrane. There's diffusion through the membrane, and it exits at a lower pressure over here. So again, we have the flux of molecules given by Mr. Fick, and there's the concentration gradient driving force, the difference in these two numbers. We are in the Henry's law regime, so this number is related to this number by the pressure and the Henry's law constant. That's the solubility. And if I put this number inside of this equation and rearrange it, I get the flux as equal to the diffusion coefficient times the solubility times the driving force divided by the thickness of the membrane. So this is called the permeability of the membrane. It's the characteristic. If you look up in a book, membrane science, and ask, well, how good is a membrane, they give you the permeability. Or the permeance if you take away the factor of L and scale it in. So this number is really important. You understand that the flux of molecules through depends on the product of two numbers, the solubility and the diffusion. Yeah? And which can be scaled by the thickness of the membrane or not. So permeability is a combination of both adsorption and diffusion. So the permeance of CO2 in membranes is governed by the product of what properties? The diffusivity and the solubility. Yeah? Yes? Yes, reverse osmosis, yes?
Membranes also have problem of fouling?
Yes. Yes and no. The good news is they don't have the physical fouling that's typically associated with seawater in these membranes, and you get junk on one side. The difficulty with flue gas is the impurities like sulfur dioxide. They're very reactive, and they can degrade the membrane. So this is one of the chief challenges. But if the membrane is really cheap and easy to manufacture, then discarding it is actually not a problem. And we'll see how that works out in just a minute. Okay, everybody got that? It's an important thing to know today. Right? So the units for permeability are very elusive. And I don't want to say too much about it, but if you're a student in this area and you look up permeability and you get a number like 7,600, the units are called bearers, and they're named after a famous dead person. And they're really difficult to figure out. So let me just say that the flux, which is a certain number of moles per surface area per second, and then you have pressure. It's usually in units of force per unit area, length in centimeter, the driving force in pascals. And if you put all these things together, you wind up something that's different than the barer, which is 1 barer is 10 to the 20th square centimeter STPs, and so forth and so on. You can look at it in the notes. I just want to say that it's really opaque, and that students and professors who are doing membrane science often get tripped up over the units. So here's a membrane with one component. Here's the feed. It's more soluble in the membrane. And here's our pressure driving force. And here's the other side. So question for you. Will a larger thickness increase or decrease the total area of a membrane you need? So remember, you're processing hundreds of cubic meters per second of flue gas. And so if you make the thickness thinner, the flux increases per unit area. And that means the total membrane area is smaller. And that's the total cost and size of the instrument is smaller, and vice versa. So a thinner membrane have higher permeance, less area. And so what you find in the literature is people are targeting 100 nanometers as the thickness of the active layer. 100 nanometers, that's 1,000 angstroms, that's a very thin layer. And so the manufacturing of these kind of membranes is a challenge. How about with two components? Let's imagine a 50-50 feed of nitrogen and CO2. CO2 is selectively more soluble in the membrane, and so CO2 goes up here. Nitrogen is less soluble, it goes down here. And so you see in the end, the permeate in the end is very much enriched in carbon dioxide. And the separation happens because, first of all, this is more soluble, and you see the slope here is flatter than the slope here. That's your diffusion coefficient. Solubility and diffusion are the things you need to know and love to do membrane science. So it's actually easy to remember. Let's talk about diffusion for a moment. Cats actually swim very well in water, if you've ever seen that. But as you probably know, cats are not very soluble in water, if you know anything about cats. So while you would think that cats would move through the membrane well, they're not very soluble. So it's a way to keep in mind the difference between solubility and rates of transport. In most polymeric membranes, the diffusion coefficients are very similar. And it's really the solubility that matters, hence my illustration with the cat. And so most of membrane science is aimed at enhancing the solubility of CO2 inside the membrane. And the transports are more or less the same. So, now you've designed your membrane, and you have it in some elegant structure, but let's just take a flat surface. And so I have the flue gas coming in, and downstream, what's the right thing to do? Should I put a vacuum downstream to pull the CO2 through, or should I pressure the front end to push the CO2 in? So you're talking about compression versus pumping a vacuum, and which is the better way to go? So certainly compression is cheaper, it turns out. We know how to compress gases very well. And so that's a good idea. And if we pull a vacuum, we'll have only a CO2-rich permeate. And if we compress, we have to compress both gases. See, downstream, we only have to vacuum one. So there's an advantage there to vacuum. Nevertheless, much of the industry relies on compressors. And here's a picture. These are enormous, these devices, and they're quite expensive. And they can be half the capital cost of a membrane separation unit and most of the operating costs. So, nevertheless, it's interesting that compression dominated the field for a long time. And so, really, the goal is to lower the energy consumption in order to do carbon capture. So I'm going to review, very briefly, 6 ideas. I'm only going to cover 4 of them, or 3, that some people in the United States who work for a company actually sat down and said, let's see if we can rethink how to do these membranes. So, for example, here's a process flow diagram. Those of you who are engineers. This represents the membrane. Here's the membrane here. The gas comes in up here, and it's been pressurized by this turbine to 5 atmospheres. And so CO2 comes through the other side, and if you solve the equation for a typical membrane, you get almost 30% CO2 at 1 atmosphere. And the stuff on the high-pressure side is recycled back to an expanding turbine that generates a little bit of power, and there's a little bit of CO2 coming out. So here's the costs here. The total energy is over 100 megawatts for a 500 megawatt power plant, and the membrane area is over 1 million square meters. That's pretty bad. That's 20% of the electricity production for a 600 megawatt powered plant. So the idea that Richard Baker and his colleagues had was, let's use vacuum instead of a compression. So here's that picture. Here comes the flue gas at 1 atmosphere, no compression, a little blower to just move the gas along. And now downstream, we're going to put a vacuum pump. And we get the same enrichment of CO2 as we did here. And look, its energy is half that, and the membrane area, though, is a little larger. Yeah? But nevertheless, in terms of energy consumption, the vacuums were a good idea. Another epiphany that was delivered by this community is to ask, what's the best way to flow a gas over a membrane? So if the membrane is flat here, flow the gas along here. But that's actually not how it's done. It turns out that's not the most effective way to maintain the largest gradient of concentration between one side of membrane and the other. There's a whole bunch of different ways to flow the gas. And so if you imagine now that the membrane is not a flat sheet but a cylinder, and I have one gas coming in here, and the exit coming out, and then another one perpendicular coming through the tube, that's a much more common way to do that. And you can rearrange all these flows. Engineers know how to do this. And the vacuum technology gave this, and they added these improvements in flow. And look, we've decreased the energy consumption even more, and now it's half the surface area. And look, we're already up to 40% CO2. That's not quite halfway to the goal. Very impressive. Okay, what else did Richard Baker and his colleagues decide to do? What they said is, rather than do this with one membrane, let's do it in two stages. And in one stage, I'll have a huge flow rate, and I have to process a lot of gas. And I'll make the selectivity of that membrane for CO2 less than optimal. And then the second thing will process a lot less gas, and so I can make the selectivity much higher. And in so doing, look, they get 97% CO2. This number is normalized to a different unit, so don't pay attention to that, but you do get 97% CO2. So the last idea they had is really clever. This is how complicated it gets. You don't have to understand all the details, but let's just walk through. Here's your burner. You remove the particles, and here you blow the gas over the first module, lower selectivity, and here's the vacuum pump. And then you'll pull the water out. That's easy to condense. And you compress it, and there's your liquid CO2 for sequestration at 90%. But the residual gas that comes off here, it goes to the second module. And rather than pump a vacuum over here, the authors came up with this idea, let's just take plain air and sweep it through. The difference in concentration of CO2 here and here is large because air has only 400 ppm of CO2. And this particular stream has about 2%. And so by doing that, they get a whole other set of contributions with this air sweep. And they feed some of the enriched CO2 back into the boiler, which makes the CO2 concentration higher, which improves the permeance here. And they make use of the water. Here's the answer. 16% of the power plant to produce CO2. Remember, we talked about 14% as the thermodynamic minimum, and the current amine processes are 30%. So if I were a betting man, and I was going to make a prediction as to which carbon capture technology is going to pay off in the long run, there's your answer, membranes. And that's why it's at pilot scale, and that's why the U.S. Department of Energy is focusing a great deal of their research efforts on pilot scale membrane science. Very exciting. So the U.S. DOE now funds it. So in summary then, the membrane separations for carbon capture really are limited by the pressure drop you can achieve with these huge volumes of flue gas. Remember, we fill the Empire State Building a few times an hour with just one power plant. Permeance is determined by diffusion and solubility. The most selective membrane turns out not to be the best. We didn't talk too much about details, but very clever process engineering can be used to achieve the best possible separations. So membrane science is really the way to go. And Richard Baker, reaffirmed that to make the better membrane, you didn't have to be a genius. You didn't have to invent warp drives or nuclear fusion. What you had to do is be very systematic and careful. I understand what's happening in the membrane, and I engineer and design them very well. So what I've tried to show you so far is that carbon capture can happen in three ways. Absorption into a liquid, off the shelf, ready to go. Adsorption onto a powder, opportunities for materials research not yet ready to deliver, at least for coal-fired power plant. And then membrane science has delivered really astounding engineering breakthroughs and is nearly ready to go. I just mentioned adsorption because while it's not competitive or feasible for direct capture, capture from a coal-fired power plant, it turns out for very dilute concentrations of CO2, adsorption turns out to be the way to go. The membrane areas are just too large. And so that reminds us that capturing CO2 at 400 ppm from the air is actually something that adsorbents can do. Another application of adsorbents that's emerging is the use of mitigating CO2 in spacecraft, in submarines, and increasingly in building design. So if it's very hot outside and you invest in air conditioning for this building, what you're doing is you're taking air in and then you're pumping that cold air out. Wouldn't it be nice if you could recirculate a lot of that cold air? Well, what has to come out of the air in order for us to recirculate? CO2. So there's a considerable application in those areas as well. So that concludes the carbon capture part of where we're going. And now the next thing we need to do is talk about sequestration. So I'm going to get started on that. We'll get 10 or 12 minutes into that before we take our break. Okay? So let's go to geological sequestration. Now, we used to have some geologists in the room. Are they still here? Yes? Oh, good. Thank you. Thank you for staying with us so long. So we've imagined these great technologies. We're compressing CO2. It's in the pipeline. It's supercritical. And where do we go and what do we do with it? And so the idea is to use geological sequestration. Let me just say at the outset, because I know there might be some critics here, how come Reimer's not talking about putting CO2 in the ocean? That's because nobody's talking about it anymore. It's a really bad idea. Okay, let's leave it at that. Okay? If you want to talk to me more about that, we can say that privately. So nobody's talking about putting CO2 in the water, seawater. Okay? We are talking about is making rocks. And so remember from these diagrams that as a function of depth into the earth, by the time you get about a kilometer underground, CO2, the natural pressure is that associated with supercritical CO2. So that's the fluid we're talking about underground. And we need to understand the relationship between CO2 with its rocks underground. And so I want to remind you of this other picture of Amritsar. The reason we are removing nitrogen from the flue gas is to decrease the area associated with sequestration of CO2. But you recognize it's a big number. And it represents a significant impact on the geology underneath the site at which you're pumping it. Really? I mean, are people actually imagining doing this, considering the volumes? So here's the point source emissions from a coal-fired power plant, from the USA for CO2, and that's the mass, that's the volume, and it's supercritical CO2, so it actually floats on water. And here's the amount of water the U.S. injects every year underground in order to either create power, but more importantly, to push more oil out for us to drive our cars. So if you look at these numbers, you recognize that we are already pumping underground a significant amount of fluid. So it's not a new notion that we would pump fluid underground. It's a notion that has already been exercised already. What about the scale of this sort of thing? This is a simulation. So this is distance in kilometers. So we're looking at a map of a part of the U.S. In the state of Illinois, in the center part of the U.S. And here you have wells, and you're puncturing, putting CO2 underground. And these are simulations on a computer of the pressure underground as a function of position in time. 100 years after injection, this is the high-pressure plume of CO2, and it's in units of 12 here. And that's, I can't recall exactly what the units are, but you see it falls off. And you're probably asking yourself, that's a huge impact underground. That's completely unprecedented. And the answer is no, because here's the data for groundwater that has been pumped under that same basin. And you recognize there's the high-pressure region right there, and the length scales are on the order of the same. So again, we've been pumping water underground for a long time. We've been measuring the physics of water underground. We understand that it's possible, and so putting CO underground at these kind of industrial scales is not unprecedented. So what we need to know now are the four main mechanisms by which CO2 gets trapped underground. And of course, it's essential that we keep it there. We don't want a big plume of CO2 coming to the earth. We'll come back and talk about safety in a few minutes. So remember my picture, CO2 is pumped underground, and it exists there as a fluid. And this particular material here is called caprock. And what does that caprock do? So what we've done here is we've put CO2 into this region underground, which is largely brine, salty water. salty water and porous rock. And above it is this cap rock, which has very limited permeability. And so it stays underground at first because it can't go anywhere in the cap rock because the cap rock has holes too small to let the gas through. But you see, I've drawn this so that because supercritical CO2 is lighter than water, it's going to float uphill. And I've drawn that deliberately because that's likely to happen in the real world. And so, aren't you worried about this? I'm not. Maybe you are now, but hopefully you won't be worried as we move through this. So the first thing that happens, there are 4 mechanisms for this to stay underground. And the first thing that happens is called stratigraphic trapping, which is to say it just is blocked from going uphill. And so here's a picture of our CO2 plume in this brine aquifer, and it's trapped. So the first thing you need to do as a geologist is understand the geology underneath you and ask where are there layers of rock which have cap rock, say more about its chemistry in a minute, and porous, briny material underneath it. That's the target place where you can put CO2. Here's another picture of that. Here's the buoyant plume of CO2 in the brine aquifer, and right above it is here's the aquifer, and here's the cap rock seal. And it's even possible in some cases where the cap rock has a V shape, and so that's a natural place to put CO2. Why do we know about that? Because it's the natural place where oil accumulates. So whenever we pull oil out of the ground, it's probably a geology that's very, very similar to this. So for every well that we take oil out of the ground, it's a likely target for us to put CO2 into the ground. The next mechanism is called residual trapping. And this is an interesting one, and I'll show you a movie in just a moment. But of course, what's happening is the CO2 is going to float uphill, and behind it, the salt water intrudes into it. And so what you wind up doing is creating trapped bubbles of CO2. Here's a movie. This is a pore in a rock, and this fluid in here is water. And what you're going to see is CO2 come through this pore. So here comes the CO2, and it displaces the water, or brine, and there's the CO2 moving through. And then the brine next behind it, and because of differences in surface tension, you're left behind with a little droplet inside. That's a CO2 droplet embedded inside of this water. Okay, that's called residual gas trapping, and it occurs first after we've pumped it underground. Here's a picture here of a prediction of the CO2 saturation in a reservoir 10 years after injection, and you can see the concentrations of carbon dioxide in these bubbles, and then here's another cartoon which shows this residual trapping. What else can happen? The thing that should be most obvious to you is the CO2 dissolves in the brine water. That's just like the process by which we make soda water, and that's called solubility trapping, and the CO2 slowly dissolves into the brine. And then the last step is that the CO2 reacts with the rocks to form minerals like calcium carbonate, and those minerals will stay forever underground. They're lost to the atmosphere then forever. So that's the last step. And so the last slide before our break, actually second to the last, because I want to show one other thing. This is how much trapping occurs, how much capture occurs as a function of time in years. And so when you first inject a well, it's this structural or stratigraphic trapping that keeps the CO2 underground. And then it's necked off into these little bubbles that are residually trapped. Ultimately, they dissolve into the brine. It takes even longer. And then ultimately, they're trapped as minerals. And of course, as you go further down in time, the security with which the CO2 is stored increases. Mineral storage is the end point. It's secure for eons. And along the way, there are opportunities, which we'll come back to in a few minutes, for environmental risk, which we have to look at. So these are the 4 mechanisms. And just before your break, let me just go to my review questions for you. There are 4 mechanisms to trap CO2 underground. Name one. Okay. Well, it could be residual trapping, solubility trapping, mineral trapping, or stratigraphic trapping. Yeah? And so that's a review question for you to consider. Let's take our 15 minutes now for a cup of tea, and then we'll come back and continuing talking a little more about geology. Yeah, low-hanging fruit. That's an English expression. Do people know what that means, low-hanging fruit? Low-hanging fruit? When you go to pick apples from the tree, the first ones you pick are the ones that are hanging low. Yeah. The use of CO2 in enhanced oil recovery, I mean, we do that already. It's an industrial process. Here you see CO2 being pushed into one particular cavity and oil being withdrawn. Using deep saline water reservoirs, sometimes offshore. One of the best demonstrations of carbon capture is done offshore, Norway. I'll say more about that in a minute. You can also go into coal seams that are unminable. That is, we're not going to dig that deep to dig out the coal, so we'll pump CO2 in there already. You can use CO2 to enhance methane recovery and various other schemes. So these are the strategies by which you would put CO2 underground. So what about the capacity? So several of you asked me at the break, really, is there that much space underground for this? So here's estimates, a low and high-end estimate in terms of gigatons of CO2 that can be stored. In oil and gas fields, in unminable coal seams, and in these deep saline formations, which Professor Reimer likes so much. So in terms of the storage capacity, minimally, you see you have well over 1,500 gigatons of CO2 capacity. The higher estimates go much higher. The number of deep saline formations that exist in the Earth is unknown. But it's estimated that there could be a lot. So this number, which is 10 to the third, could be 10 to the sixth. So right now, the human annual production of CO2 is 31 gigatons per year. So you compare that number to these numbers, and the answer is, even with the lowest estimates of storage capacity, we have the capacity to store CO2 for a very, very long time. So where are we going to do that? Our friends, the geologists, can map the Earth, and they can tell me that in these kinds of basins, we are likely to find the kinds of rocks that hold brine aquifers, the ones that I find so attractive. And you can see that there are many places around the world in which this can be accomplished. In the United States alone, it turns out we have one of the richest environments for putting CO2 underground, which is a good thing because we generate the most of it. And here you have these maps here. The dark blue shows regions that are untapped as of yet, and the red areas are currently being tapped for either enhanced oil recovery or sequestration, which I'll say in a few minutes. So where? Much of the Earth, particularly the United States, where we produce the most CO2. So what does that mean? It means there are already projects in play. People have not been sitting on their hind legs. There's a whole host of projects, and I'm going to mention a few in particular, but I want you to note Weyburn, Insula, and Sleipner in particular. The volumes are small, on the order of a megaton per year, but nevertheless they demonstrate the physical principles, and you recognize that most of the current ones are all aimed at enhanced oil recovery. As I said, enhanced oil recovery is this awkward partner for carbon capture because they're actually used to generate more CO2 to get oil out. But the geology and geophysics of doing enhanced oil recovery really goes hand in hand with CO2 sequestration. In fact, it's very interesting to go to these international conferences on carbon capture, and a third of the audience will be people who are doing enhanced oil recovery. And the environmentalists, like Reimer, is sitting there with the people from Exxon, and it's a really exciting tension. So there's already megatons per year being stored in these projects. Let's take a look at a couple of them and see what they're doing. So here, this project in Weyburn, there's CO2 being captured from a coal gasification facility in North Dakota. That's sort of in the north part of the United States in the center of the country. And then there's a 300-mile pipeline which goes across a border into the country Canada, where at this Weyburn facility, they put CO2 underground to get more oil out. So it's really the first project in which anthropogenic CO2, that is CO2 produced by humans, is being used for enhanced oil recovery. And it represents a demonstration that this sort of thing can be done, and it can be done across borders. The Inshallah project is in Algeria, and this is a particularly interesting project because you have natural gas wells in which the natural gas is on top of a brine aquifer. That natural gas is being sucked out, but the natural gas has a significant amount of CO2 into it. And remember, we talked about sweetening at the very beginning of the absorption section. So you have a processing facility, which is an amine absorber, which is taking CO2 out of this stream and then injecting it sort of further downstream into the brine area. And the Inshallah project represented really a first demonstration that carbon injection could happen downstream from a gas production well. Unfortunately, this project was ceased because the people doing it really lost their incentives to do it. The Sleipner project is the most important for us to know about. It's in the North Sea, so there's a facility offshore the coast of Norway. That facility is pulling methane and out of the ground, and oil and methane out of the ground. There's a facility which processes it, amine absorption, and the CO2 is re-injected into a brine formation that's well above it. This project has been in play for over a decade, and as you can see, the formation has a very large capacity because it's huge, and we've already put 11 megatons of CO2 in that facility already. It's highly monitored. The geophysics literature is filled with seismic and other studies of where the CO2 is and how it's progressing in time and how it's moving from fluids to bubbles to solubilized CO2. It's really a very exciting project off the coast of Norway. And it represents the prototype of what we could be doing worldwide. But, and I have a few slides, now that we have to be honest with each other, we're all good friends, so let's be honest with each other. What's the problem? Why isn't this progressing further? It's because carbon capture, particularly carbon gas storage, CGS, has received a number of very negative publicity in the media. So one particular facility for capturing carbon from a coal-fired power plant in Canada was shut down. It has huge technical problems. The media is filled with all kinds of issues. They've had unexpected costs. Notice the 30% energy penalty. That's because they're using the amine absorption process. So this is unfortunately makes for a bad press. And then here's another article from the Wall Street Journal about Shell's project, also in Canada, in which the falling oil prices around the world have contributed negatively to the economics of carbon capture and sequestration, which is to say, if our communities don't put a price on carbon dioxide emitted into the atmosphere, then all the cost associated with putting it underground falls upon the owner of the plant. And that translates into higher prices. And in another part of the world, those prices will be lower because they don't capture carbon dioxide. And so you see this economic problem. In the second edition of the textbook, which I'm working on now, we have a whole section on the economics of carbon capture and sequestration. And the economics is, to be honest with you, completely untenable until we put a price on carbon. Only at that point will the forces of capitalism come to our service and make this happen. So a lot of politics associated with this. This was just last year. Also the amine solvent process. There's another project, a Kemper project in the United States, which hasn't come online. It's been delayed and delayed. Many articles have been written in the newspaper about these delays. Also in amine process, they're having a tremendous amount of difficulties making that happen. And even though in the United States this particular technology has a lot of political backing. Perhaps most damaging was this article in Scientific American, which is a very popular journal read around the world, English journal that's read by scientists and non-scientists alike. The cover story was about the carbon capture so-called fallacy, in which the authors, one by one, looked at these big mega projects and showed that they were technically and economically not feasible. It was a huge blow to all of us who work in this area. So what does it really mean? So let's take a look at this economic side of it, because we have to be honest with each other about the kinds of commitments it takes in order for carbon capture and sequestration to work. So here's a timing diagram, time going this way, and the cost of carbon capture in this way. And you see at the very, very beginning, the carbon capture costs are very, very high. And that's because we're still learning how to do these things. And so what is needed is considerable subsidies if you're a producer of power, or loan guarantees from the government in order to experiment with these various technologies. And then as it gets more and more successful, the cost falls because you know what you're doing. And hopefully, then the carbon price, due to our policies, will increase. And so we'll reach a break-even point where we get wide-scale deployment when the price of carbon more than pays for the unit operation cost of carbon capture and sequestration. But I need to be very clear. Without this rising carbon price, there's no way we're going to do it. So what about the time and length scales of industrial scale gas sequestration and storage? So here's a picture of the United States in which we show the various basins laid out in brown here that are acceptable for holding brine. Here's the footprint of trapped CO2 in various test sites around the country, again, mainly for enhanced oil recovery. And then there are analytical models, as this paper shows here, in which they use these mass and energy conservation equations to predict when the CO2 is in bubbles, when it dissolves in the brine. So the solubility trapping, the gas trapping, and the mineral trapping are all captured. And the bottom line is, if you look at this, is we have 160 gigaton capacity in the United States without any unusual geology or geochemistry. So let's summarize where we're at with regard to carbon gas storage. These are the four mechanisms by which this happens. We reviewed them already. This is the barrier. This is the little droplets. This is the solubility and the mineral trapping. There are known geological formations that this can happen, and there are significant problems with public perception. And that still clouds our ability to do this particular capture. Now, again, during the course of the break, several of you came up to me and said, well, is this safe? Okay, and that's an important question. So what is the permanence of CO2 sequestration? So there are concerns. So one of them would be what I would call leaky geology. That is, here's a picture of an injection well. Here's my CO2 underground, and everything looks fine and well, but there's these little minor faults. These small geological faults are not easily measured by the existing seismographic techniques. And what you could have is one of these minor faults being a conduit for the CO2 to come back up into the atmosphere. And they're very difficult to detect. Another possibility is that the wells themselves are leaky. So remember, we punch a hole underground. We have this plume of CO2. But what about the farmer 2 or 3 kilometers away that punched a well, and somebody else that punched a well? So here's a picture. I know you can't see it very well, but you get the idea. This is a picture in Alberta, which is part of Canada, and every one of those dots represents a well. And all those holes have been punched in the ground. And you assume that the owner of those holes was a good steward of that event, and when they were done with the well, they capped it properly. That is to say, they put a plug of cement inside the well, and they used the appropriate technology. Well, how likely is that to happen? Well, I can tell you an example. There was one large oil company that didn't use the right technology, and it's BP, and there was a huge accident in the Gulf of Mexico a few years ago, a big blowout of a well because this cement capping was not done properly. So how can we assume that the owners of all these wells have been good stewards and capped it properly? And the answer is we can't. And so this is a significant risk. So this cartoon demonstrates, I think, best all the risks and all the physics that's sort of happening. I like this cartoon very much. It came from my colleagues at the Lawrence Berkeley National Lab, the co-authors of the book. And so you recognize here, for example, is my CO2 injection well. And this is what I hope is happening. But, of course, here's an old well here. And there's some sort of a leak along this way. And this could deliver CO2 directly to the air. For example, there could be a fault in which CO2 then leaks back up to the atmosphere in forms of plume. There could be leaks that deliver CO2 into the groundwater. So as much as I like fizzy, bubbly water, having it in our groundwater is not a good idea for a lot of reasons. And so all kinds of monitoring has to happen. We need some special wells. We need to use seismographic techniques, satellite data. All kinds of measurements need to happen in order for us to feel secure about where the CO2 has gone. So I'm going to walk through a few of these in a little more detail, but this is the big picture for where we are headed. So the potential impacts then vary with depth, and the significance of the impact, human health significance is here. So notice a ground plume. Why are we worried about a ground plume? Because it has happened. It was a natural gas, a natural CO2 underground, a lake in Africa, and the CO2 bubbled up through a natural process unexpectedly, and about 1,000 people died. You can't smell CO2. You're just asphyxiated. CO2 is heavier than air. And so a ground plume represents the most serious hazard. Intrusion into our drinking water is a huge problem, and induced seismicity is a huge problem that have to be thought about for this. So here's an article from the U.S. New York Times about the state of Oklahoma. Oklahoma is one of the places in the United States in which these advanced techniques for recovering oil and natural gas underground, so-called hydraulic fracturing or fracking. You inject sand and water at high pressure. It cracks the rock, and then the cracks in those rocks allow the natural gas to escape. And this can be propagated because we can also drill horizontally now as well as vertically. And so a lot of media has been associated with the earthquakes that are appearing from this fracking process. And if you read this carefully, you'll see that the authors of the New York Times are concluding that we have to stop pumping water underground. Induced seismicity is not unusual. Here's where I live, right here in the San Francisco Bay Area. Here's the city of San Francisco right here. Here's where all the great wines are, right here. And then right up here is a place where we generate power by injecting water underground where it's hot, steam forms, the steam comes up, drives a turbine. Geothermal energy. It's a huge power plant and contributes significantly to California's energy profile. And these little dots represent earthquakes. Every hour or two, there's a 2 or 3.0 earthquake in that area, and it's been going on for a long time. And the reason is because if you look at what it takes for a rock to fracture, you go to a certain depth, and the rock is under a certain hydrostatic pressure, and if you add a fluid to it, you increase that pressure, and at some point in time, you exceed the fracture stability of the rock, and the rock cracks, and you get a slippage and or an earthquake. Injection-induced earthquakes are also happening in Oklahoma, where a lot of fracking is occurring. It's also happening, here's another article about a huge earthquake, road-splitting earthquake. In Switzerland, in the city of Basel, they were using a great plan for geothermal generation. Cold water underground, hits the hot rock, steam comes up, drives a generator, great idea. Magnitude 3.4 earthquake in the city of Basel, shut it down. So induced seismicity is a real problem to think about. The other, of course, is groundwater quality. So here's our injection well here, and a small fault that was undetected leaked some of that CO2, or maybe it was a well into the drinking water, and then you have acidified water, and that leads to decomposition of metals and all sorts of things, and the groundwater becomes undrinkable. The near-surface environment, as I mentioned before, is particularly upsetting. I called it earthly CO2 flatulence, but this lake in Africa is a demonstration of what can happen. Completely unsuspecting to the people in the community, a plume of CO2 appears, and death ensues. The good news, though, is that we understand a great deal about the physics of dispersion of heavy gases. So let's imagine CO2 is in air in a box, and we take the lids away from the box and ask what happens, and the gas will diffuse by passive diffusion, and the dense gas flows out amongst the edges, and that creates circulation, which winds up diluting the gas. And so if you do a mathematical analysis of the dispersion, you recognize that over really over 200-meter length scale, we're already down by a factor of 10 squared or 10 cubed in the concentration of CO2. So, that doesn't do any good if you're at ground zero, but it does suggest that the dispersion of CO2 can happen effectively. The lake in Africa was problematic because the lake was at the bottom of a canyon, and the village was around the lake, and so that's the reason the CO2 was trapped. So what does that mean? It means we have to monitor. And so now, in addition to the cost of pumping the CO2 underground, we now have to deploy instrumentation to make sure that these environmental risks don't happen. So we have to document and confirm that the storage is happening. That's almost certainly seismography and those kind of mechanisms. We have to have mathematical models to match the data so that we can understand and predict what's happening. We have to anticipate that leakage will happen, and therefore we have to figure out how to measure it. And the way to measure it is on the surface and on the subsurface. So here's a slide that shows a few of the things that we would like to deploy. So here's your injection well, and this is what you think is happening. And then you need some monitoring wells. Here's a deep one in which there are devices placed along the way, and they can be seismic, they can be pressure, temperature, composition, and so that you can have seismic waves generated on the surface. They're reflected at these measuring points, and you can discern the plume of CO2. I didn't bring any of those slides. Some of them are in the book. The technical details are a little heavy, but it's actually quite fascinating that you can image on the kilometer length scale these plumes of CO2 by having microphones underground and setting off explosions on the surface, or just having a metal rod slam against the surface. That's how sensitive these things are. And of course, you definitely want to have simple CO2 detectors on the surface. And so, these are all the tools that we need. So the challenges then for monitoring is we need to monitor for long periods of time. If we're going to pump CO2 underground for 50 years, we need to monitor probably at least 50 years after that happens. We need time resolution. We need reproducibility. We need space resolution. It has to be cheap. And the sensors have to last, for example, underground in brine at a pH of 3.5, 100 and some odd degrees C, and 40 megapascal pressure. So if you're a chemical/electrical engineer and you make sensors, just think of that kind of environment and you recognize how challenging it would be. Nevertheless, there are deployments already of these kinds of monitoring schemes, and they can work. So there are significant problems with the public perception of CGS. That's only going to be solved when it's done successfully, and that probably means not using a means. The environmental risks are known and require substantial monitoring, and this is an additional cost to CGS. That's a cost you and I will have to bear either directly when we buy power from the power company or indirectly through the use of a carbon tax. So that's all I would like to say today about geological sequestration. And this allows us to turn to the last topic, which is what other schemes do we have in mind for mitigating climate change? Obviously, dealing with CO2 is only one of them. So let's spend a few minutes together, you and I, maybe a half hour or so, and maybe longer, depending how quickly I speak. And I know Professor Singh wants me to slow down. It's hard for me to slow down. I love this topic so much. Let's talk about climate intervention and negative emission technologies. So climate intervention means that I want to step inside of the planet and figure out a way to deal with climate change. And remember, I showed you this lovely circuit, which is a way to think about our role. So here we are. You and I have made a decision that for our family, for ourselves, to honor God, for whatever reasons, we've decided to make some efforts at conserving how much we buy and consume. We've decided that we will consume less energy and build efficient devices. And we've decided to deploy low-emission carbon technologies, and in particular, perhaps carbon capture and sequestration. So that's what I call the mitigation side of the ring. But there's another way, and that is we say, climate change is happening, it's going to happen, and let's develop intervention strategies that decrease the amount of CO2 or the impacts of climate change. Same goal, different way to go about it. These people have given up and are ready to change the planet, and these people say, no, we can fix it all. Okay? And we all get along together. So what about solar geoengineering? If the planet is warming up, why don't we cool it down? So there's interesting ways to do that. So climate intervention, let's look at these words carefully, seeks to produce a change in some aspect of the climate. So for example, the temperature. And that includes something to remove CO2 or other greenhouse gases from the atmosphere, or to change the Earth's radiation balance, and sometimes referred to as albedo modification. This is not the same as capturing CO2 from a coal-fired power plant. So it's this part of it that we want to spend the next minutes talking about, which is these intervention strategies. So one way to imagine intervening on behalf of the planet in terms of the temperature is to shield it from sunlight. So one way is to put aerosols in the stratosphere. We could use satellites to put giant reflectors in the orbit. We could inject chemicals to affect the ozone balance. We could seed clouds to make more clouds appear and thus reflect more. These are all strategies that have been discussed, in some cases in great detail. And we're going to come back and look at some of the challenges. But you can imagine for a moment the cost of putting giant reflectors in orbit. And what is that going to take? And I'll show you in a minute a calculation for how much sunlight would have to reflect. How about aerosols in the stratosphere? There are a lot of our community that are interested in using aerosols as a mechanism for either capturing carbon from the air or as a mechanism for reflecting light. And the answer to that is if you sit down and calculate how much aerosol you need per cubic meter of air to accomplish your goal, and then ask, how do I get it up there? Well, I put it on a plane, put it on the plane, and it comes out the back of the plane. And then ask how much CO2 is associated with taking the plane up into the air and flying it around and dropping the CO2 off, dropping the aerosols off. And you recognize that you have to be very, very careful about this sustainability. We've come back to this word several times. Is this actually really sustainable? Do you heal the planet or you do more damage? And the answer is it's not obvious. You have to engineer and understand these aerosols very carefully before you can accomplish that. So solar radiation management works by reflecting visible and ultraviolet light before it gets to the Earth, increasing the albedo, and thereby changing. And I already mentioned aerosols and reflectors and cloud seeding. So how does that work exactly? This is the picture I showed to you before about the radiation management of the planet Earth. Here's our incoming solar radiation. And it's 340 watts per square meter, and the reflected is about 100, so 240 is the net input. And some of it is absorbed by the atmosphere and the ground, of course. So 240 watts come in by the Earth's atmosphere. Radiative forcing due to anthropogenic CO2. We saw that exciting experiment in which that was actually measured. Turns out to be 4 watts per meter squared. So if I want to mitigate the heating from that, then I need to reflect this much back, or 1.7% of the incoming radiation. So it turns out that's a big number. To modify, to put a sunscreen out in space that gets the 1.5% of the sunlight is no easy feat. And that's also a lot of aerosol, unless it's really carefully crafted. So that's a significant problem with geoengineering. Let's talk about CO2 removal. So this is this strategy that I alluded to earlier on, which is the cost for removing CO2 from the air is really high energetically. But at some point in time, it might be worth paying. And can we think of the various strategies in which we would take CO2 out of the air? And there are 4. And we should consider them in some detail. How do we remove CO2 from the atmosphere? So this is this climate intervention scheme in which we have carbon dioxide removal methods, the goal being to reduce the level of CO2 so that radiative forcing is mitigated. So here's our schemes. This is a cartoon that shows exactly what you could do. Let's fertilize the ocean so that the algae in the ocean takes up the CO2 from the air. The algae die, sinks to the bottom of the ocean, and we're pulling CO2 out of the air. Or we could increase the alkalinity of the ocean by pumping sodium hydroxide into the ocean and thereby increase the solubility of CO2 in ocean waters. Let's put some chemicals on the rocks so that CO2 and water react with those chemicals much more quickly than they do already. This is called accelerated weathering. And remember when I talked about the carbon cycles? One of those geological cycles was to take CO2 from the air, react it with minerals, get into the ocean, subduct it underground, and that's part of that cycle. I could do direct air capture, right? This is what everybody says is crazy because it takes so much energy. How about if I just plant trees? Wouldn't that be good enough? Let's just plant a lot of trees. Or I could use trees to make energy, and in burning the trees, rather than let the smoke go into the air, I pump the CO2 underground. This is so-called BECCS, biomass energy with carbon capture and storage. So I'm growing trees, cutting them down, burning them for your power plant, but the CO2 goes underground. It's called BECCS. All the people who are really keen on this are really featuring BECCS. So we enhance the natural uptakes one way or another, or remove it directly from air with our clever chemistry and chemical engineering. It will take decades to affect the climate because these are slow processes. Okay, how about enhancing the natural uptake? So here's a complicated slide which again shows the rates. These arrows show the rates at which things are moving. So here is fossil fuel and land use changes dumping CO2 into the atmosphere. 9 petagrams per year. And then here you have the CO2 coming down and going into the ocean or being taken up by trees that are growing. And so 5 petagrams per year are absorbed by the land and the ocean biosphere. So let's change the land management. Let's accelerate the weathering, fertilize the oceans. And so we have these 4 ways to suck carbon out of thin air. I mentioned one of these already, bioenergy with CCS. That's one way. We could grow more trees, so-called afforestation. We can capture directly from the air, or we can enhance the weathering. So these are the 4 schemes that we need to consider when moving forward in this review. So let's talk about afforestation. That is to say, I want to plant trees where forest does not exist. And the trees and vegetation consume carbon dioxide. They grow. It's totally passive. It's easy. It's expensive. All it requires is a lot of land that's not being used by something else. And maybe, if you don't do it correctly, the land that you do use now has to have fertilizers and water, because not all trees grow everywhere well, or for that matter, grasses. The idea, though, is that it's nice and passive because everybody loves trees. I know Vice Chancellor Brar loves trees, and so your campus is therefore so beautiful. So, happy Earth Day, let's plant a tree. But there's some issues with that. Okay, so if you do that, our current emissions estimate predict that about a gigaton of carbon could be accounted for if we plant more trees. We could remove 3 gigatons from the atmosphere through net growth and absorbing most of that from fossil fuel burning and deforestation. Exactly so. It's not like you can grow just anything. It has to be engineered. Yeah. Right? That's the word I like to use.
Trees like Ficus religiosa and Ficus belangensis have capacity to assimilate carbon dioxide more than any other tree.
Yeah, miscanthus in particular.
And I think plants which bear oil and carbohydrates are more beneficial than any other, because carbohydrate has C6H12O6. They can convert 1 carbon into 6 carbon, and this way we can sequester carbon dioxide more easily than any other strategy.
Yeah.
Oils at the same time are high carbon compounds.
And these are all strategies that people are thinking about, and they're all
parking
good
areas
ideas.
will not be inside the institute.
Sorry?
Parkings parkings of automobiles and
Yes.
It should be outside the campus.
Outside.
So the content of particulate matter inside the air is inside the campus is high as compared to the other side.
Yeah. So there are advantages to engineering the trees for the purposes of the regional environment, which is exactly correct. We do have to be a little bit careful, though, okay? Because ultimately trees die. And when they die, the microbes get them, and that ultimately it comes back into the air. Growing a lot of trees works for a decade or 2 or 3 or 4, depending on the tree. But unless you do something with the trees, sooner or later, the CO2 will come back. Okay? So we all just want to make sure we understand that. The agriculture sector in the world could be carbon neutral if these practices were widely adopted. That is, the management in terms of not in producing the highest crop yield, but in terms of producing the least CO2. And it's estimated that the air would be lowered by 40 to 70 ppm, and that's possible by the end of this century if we deploy all these techniques. Professor Reimer is frustrated again by his electromechanical devices. I've already gone through 6 batteries in my laser pointer, and I'm really quite annoyed. I must have bought cheap batteries. Speaking of not sustainable lifestyle. We'll keep trying. Yes, suboptimal. You notice Professor Blumick and other colleagues are not using laser pointers, they're using the pointers on their screen. That's because they're better than I am. Okay, so let's move forward. So what's one way around this problem of having the CO2 escape? And this is bioenergy combined with carbon capture and storage, BECCS. And this is the process by which that many people think is the most effective, and it's a very growing research community. And the idea is really relatively simple. You grow trees or miscanthus or other kinds of plants, and you burn them, and then you take the CO2 from that combustion process, capture it with the technologies we've been talking about, membranes, adsorption, absorption, and then put it underground. And so what you're doing is taking CO2 out of the air and putting it underground. It takes a decade time scales to have an effect, but nevertheless, you could produce power in a way that's carbon neutral or even carbon negative. So these technologies are known to exist. That is, we've been burning wood for a long time to generate power, and we certainly know how, in principle, to do the carbon capture and sequestration. The problem, of course, is you have to look at the land area. And as your colleague over here pointed out, not every tree is the same, and the amount of area you need is enormous. So if you make a bad choice for the kind of tree, you could wind up having half the country of India growing grasses just to sequester the CO2 necessary to have an impact. And that's certainly not something that your country, and for that matter, mine, can afford to do. The process is really quite simple. In typical fossil fuel burning, of course, you just take CO2 out of the ground, and carbon, and put it into the air. And there are, strategies for minimizing that effect. But biomass really gets around this with the net zero emissions. And then if you add the carbon capture, then you have a net negative emissions. And by the way, the energy that's produced from the biomass can be used, and we're going to say more about this in a minute, to produce biofuels. So liquid fuels, gas fuels, all kinds of chemicals can be produced from biomass. So there's a significant amount of our scholarly communities that are focused on taking cellulose and wood and grass and taking it all the way to the fine chemicals that are used, that are currently made from taking oil out of the ground. So that's another opportunity and another reason why BECCS is a particularly interesting process. It's already displayed. The technology is already known. This is a picture from a plant run by the Arthur Daniel Midlands and Schlumberger, two huge agribusiness companies. Here's a little picture of the United States in Illinois, Indiana, Kentucky, and they take corn and convert it to ethanol. The ethanol market in the United States is driven artificially high by its inclusion in transportation fuels. They capture a megaton per year of CO2. They transport it to a sandstone formation, and they're pumping CO2 underground. So BECCS can happen. It works. And here's a demonstration plant. Although taking corn to ethanol turns out to be not a sustainable way to produce energy, but nevertheless the plant is well demonstrated. Another possibility is to take biomass directly to fuels, and so we might grow miscanthus, which takes up CO2. We have cellulosic biomass. It undergoes some kind of treatment. Enzymes digest it. We produce sugars. The sugars are used to grow microbes. The microbes produce, for example, butanol. Butanol is then a very effective fuel. Okay? So that whole strategy looks particularly good. Unfortunately, this requires a huge amount of energy to break up biomass, and that's sort of problematic. And if you look at this from the point of view of ethanol production, so here you have the input. Miscanthus is it's okay. Okay, yeah. Forest residues, wood chips, and so forth. There's the treatment. There's a hydrolysis. You get the sugar, conduct fermentation, do distillation, dry it, and you produce your ethanol. And there are sugarcane, corn, and cellulose are the possible resources. So that's a possibility. It looks like a way to introduce fuels. But let's take a look at how much energy is used. This is a particularly interesting paper from the Climate Intervention in the National Academy Press. It's for free. You can get it on the internet. And then Sally Benson, my colleague at Stanford, wrote an editorial about this, calling attention to the fact that if you look at the various steps along the way, CO2 comes in to grow the switchgrass, but the farm takes a little bit of energy. And then you have to transport it to the plant, and that takes a little bit of energy, and you lose some of the biomass, milling it down to the point where it can be fed, and then processed, in which you use a lot of energy. And then, the capture isn't perfect. And you reach the end and you realize that the CO2 actually, about half to 1 gigaton of biomass is needed to capture a gigaton of CO2. And so that's harsh. It's a harsh energetic process. And so researchers in our communities are looking at these at every step of the way, and in particular a lot of enzyme engineering and other technologies, ionic liquids and so forth, to try and minimize these losses in energy. How about how much biomass is available in order for us to conduct this? So here's the price in U.S. dollars and the quantity of biomass available. And you can see the biomass can provide, if you add all these numbers up here in this graph, 2,000 petajoules of energy in 2030, which is really quite substantial. And you can look at the quantity available and look at their various feedstock types and recognize that we have an extraordinary amount of waste that we currently don't use, that we could use. There are dedicated feedstocks that they start to cost money. And so then the cost of carbon capture becomes a little, or carbon sequestration from the atmosphere gets a little bit higher. The land mass use is particularly problematic because not every place is suitable for growing the crops we need to make fuels. So here's an International Panel for Climate Change projection. This is to achieve the Paris goal, which we started off with the very first lecture in the class. That is to keep below 2 degrees C. So this is the amount of atmospheric CO2 that has to be removed by 2100. And then you look at the various attributes. Let's just take abandoned land, the land around Amritsar that's what had something on it but is now abandoned. Let's take some of the forests and convert them into cropland and so forth. And you recognize that pretty quickly we run into the situation where we can't achieve the Paris goals because we don't have enough resources in terms of land. So the future is not completely clear as to how to implement this. And the best predictions I've read is that locally there are some places, some regions, perhaps in India and other countries, where this makes a lot of sense because locally there are resources and land available to do bioenergy. So in summary, for BECCS, about 7 to 9% of our electricity demand could be made this way. It's a significant reduction of CO2 emissions. Really, the value lies in the sequestration of carbon from biomass rather than electricity. We could convert to liquid fuels. That also reduces the impact in the industrial sector. We create nice forests or regions if we engineer this properly. And there are certainly societal benefits to having a lot of trees around. Here's the kicker, though. We need land, we need water, and in some cases fertilizer, and there could be significant damage to an ecosystem if we replace a natural and, quote, unproductive ecosystem with something that's completely engineered for our purposes. And this is a greater philosophical question about what value land has and what roles we want to play as humans in engineering the land to make our lives better. It turns out in the United States, 6% of the land area would be required to capture 1 billion tons of CO2, or 1/30th of the world production. This may not look like a big number to you, but I tell you, let's go to India. Let me just say to the leaders of India, would you please give me 6% of the land for this particular process? And I have a feeling it would be challenging. There is another option with biomass that's really quite interesting, and it's this notion of biochar. Biochar is an interesting aspect. So what happens if you heat up biomass, like wood or other products, in the absence of oxygen? Okay? So what happens is you're really accelerating in real time the formation of coal, because that's what happens with coal. These plant masses go underground, and in the absence of oxygen under high pressure and temperature, it converts to carbon. We can do that naturally, and all we have to do is what's called pyrolysis, which is to say you heat plants and matter up in the absence of oxygen. And from that, you can produce oils which can run our machines, and you can also produce biochar, or carbon, and the carbon can be adapted and planted in our farms to help increase the productivity of the soil, but it is stored forever because you've just made coal out of the atmospheric CO2 used to grow. So, up to half the carbon would be sequestered if we went into the biochar business. So here's a picture of what that would look like. You use manure, compost, organic, grasses, anything you can grow. You conduct this pyrolysis. You generate some fuels. You also get some carbon back, which has a little bit of impurities, and that's returned back to the soil. So that's a process. Biochar is a process by which we could certainly pull CO2. It does, however, require high temperature and no oxygen. So that's an environment that's energy intensive. How do you get rid of the oxygen and do this process? And we've already seen for pre-combustion carbon capture that removing oxygen from air to produce pure nitrogen is a little problematic, although we can do it with membranes now much more effectively. So let's take a look at the CO2 removal in terms of gigatons per year and look at the estimates from the International Panel on Climate Change, where we are today, what could happen by the end of the century with changing how we grow our forests, burying biomass. So one way, by the way, if we grow a lot of trees, and we don't want the trees to decay and release CO2 in the atmosphere, is you bury the trees. Grow a lot of trees, take them to the middle of the ocean, dump them in the ocean, they go to the bottom, they'll stay there for centuries. Here's our BECS, and here is where you add them all together. Here's, of course, biochar. So the net picture here is that in terms of removing, remember our goal here is not carbon capture and sequestration from coal-fired power plants. Our goal here is to decrease the amount of carbon in the air, to decarbonize the atmosphere, carbon which was put there in the first place because we're using the atmosphere as our waste dump for excess carbon. So that looks like a pretty powerful thing. So burying or burning is sort of a policy issue that has to happen probably locally or regionally. So let's get to the last topic. Not really last, but the topic I want to talk about next, which is direct air capture. And this is a highly engineered process whereby you imagine enormous arrays in which air is pulled with a fan across an active medium, an adsorbent, for example, and CO2 is captured directly from the air. And then with the use of a carbonate solution, potassium carbonate, for example, you can pull the CO2 and make it into minerals. So it takes CO2 from everywhere, The advantage of direct air capture, it's completely indiscriminate as to where the CO2 came from because it's in our air. Okay? No politics involved. Low land use, right? And can be scaled to fit wherever the local opportunities are. It doesn't work yet. That's the problem. It's certainly not available on a commercial scale. And I want to call your attention to the fact that why we didn't really think about this as feasible in the first place. So you're going to have these enormous things that are going to be capturing CO2 from the air. The surface area is really quite excessive. So, but in principle, they could be built anytime, anywhere. In this lovely cartoon, you have cows on the farm and these gigantic devices which are capturing CO2. The idea is simple. As I mentioned before, you capture air. Air flows through. You take a CO2-rich solution of carbonate, which is in the device, and then you use a little energy to get the CO2 off. This is a stripper, if you like, and return the solution back again, and it runs continuously. It takes energy, and the source of the energy is important. Let's make a direct air capture system, and it's run from a coal-fired power plant. That's not a good idea, right? So you have the energy source has to be a renewable source, otherwise the whole purpose is defeated. Yeah? So that means it's ideal to place these kinds of devices where you have natural gas. Not so good, but wind, solar, nuclear, good idea. Remember why I said it was a bad idea? If you look at what thermodynamics says about the minimum work necessary as a function of the mole fraction, remember we're down here, CO2 and air, and the energy penalty is the highest of all these other capture techniques. So energy is really problematic, and that's why when I first introduced this, I said only a crazy person would invest in this. But it turns out, this is 3 to 5 times as much energy. It turns out it may not even be carbon negative, because if you look at all the engineering, all the energy use that has to happen in this system, and in particular the carbonate solutions that are recycled. So now you talked about absorption in these amine solutions as being slipping and so forth. These carbonate solutions require a huge amount of material. Nevertheless, it's compelling. And the reason we want to capture carbon directly from the air is right now, Reimer has only been talking about capturing coal from CO2 from a coal-fired power plant here. But look at all these other sectors that aren't being affected by that. And so, like I said, the great thing is that it's completely indiscriminate. It could help with fugitive emissions from storage. That is, if we have a carbon direct air capture place near where there's a well or a site for geological sequestration, if there were a flatulence, a fart from the earth of CO2, then this could help with that. We don't have contaminants, at least not in high concentrations, so the chemistry of these direct air capture devices can be more straightforward. It's already available. Submarines currently operate with carbonate solutions to remove the CO2, as do spacecraft, so it's not a new technology. It's an insurance mechanism, right, where we might be able to deal with the rising climate. And so, as a result, there are companies. Our students from Berkeley are getting hired by these companies. Many of them are startup companies, and Climeworks is one of them, in which they're building a plant in British Columbia. Here's another one called Carbon Engineering. This is their pilot scale, and this is their envisioned full-scale carbon capture, direct air capture devices. And if you look at the energy requirements, that's this column right here, you recognize they still vary all over the place, between 60 and 1,000 in these particular units, which is the dollars per ton of CO2 captured. So still a lot is yet to be known on these systems. So the direct air capture summary is that the point sources account for 1/3 of our fossil fuel. The direct air could address them all. It already works. We know it works. We know what technologies to utilize, and that's acid-base chemistry. The cost estimates vary a lot. So without a carbon price, it's probably not going to be feasible. And we could address leakage. Could be an insurance policy against low probability events. And, whether it's carbon negative or not is maybe. And that depends on the source of energy from which you get this renewable source. So the next thing we need to consider is enhanced weathering. That's the last of our 4 steps to drag CO2 directly from the air. I'm going to try one more time with my with my batteries because I'm getting very frustrated. So now I'm pulling old batteries up that have already been rejected because they weren't working. Everybody still with me? Yeah? Oh, that one works. Okay. Enhanced weathering. Remember that we have slightly acidic rain. It falls on silicate rocks and breaks down these carbonate solutions. It goes into the water and eventually winds up as limestone. And here's another. It could substantially remove CO2 in the air. We know it's part of the natural carbon cycle. We know it's been helping control the level of CO2 in the atmosphere for a million years. And so it's a very exciting opportunity. It requires an industrial scale of moving rocks around in a scale that's really quite unprecedented. And then, of course, crushing up rocks and distributing on 6% of the surface of the Earth has its own energy cost, which would generate CO2. And it has environmental costs, breathing particles. And so it could be quite high, but nevertheless, many people are talking about enhanced weathering. And the idea is really simple. Remember, we had this diagram which showed carbon dioxide, and carbonate. And the problem was the kinetics moving from this place to this place are really, really slow. So we really need to accelerate this process to form the carbonates. And this was the picture we had before, CO2 and water forming carbonic acid, which reacts with silicate rocks to get bicarbonate into the water and ultimately into the ocean. And we know the chemistry of that requires ions, and this is all review to you. It takes 10,000 years or more, and it's typically associated with about 1/10 of a gigaton of carbon per year. So enhanced weathering, let's take a look at the reactions you might imagine. Calcium carbonate, turns out in the long run it doesn't capture carbon. The olivines, like silicates, and these silicates have a net chemistry which winds up removing atmospheric CO2. So the idea is to start with silicate rocks, spread them on the ground, and have them capture CO2 and form these products. So we mine, crush, and apply silicate materials over the land surface, and they release cations during the dissolution, and this ultimately changes the pH locally, but nevertheless sequesters CO2. Carbon is transferred from the rock and atmosphere to the biosphere, and then ultimately to ocean. And the kinds of scenarios you would imagine, we could reduce the CO2 concentrations by up to 300 ppm. So this is really the most significant of all the technologies we've talked about to bring us back into pre-industrial age. There are resources available, particularly if you go to places where you have a lot of water in the air, then there's less rock available. And there are a few drawbacks, yeah? So carbon is redistributed, so it's really not equivalent. It takes time, and the cost is comparable to direct carbon capture if you look at it on a cost of CO2 per ton, which means without a carbon price and a way to distribute the money from carbon taxes to the people that want to crush up rocks, it's not going to happen. So the net transfer happens from CO2 from the air to the carbonates. It's stored as a solid mineral. It could stimulate growth because some of these minerals are healthy. And it could mitigate ocean acidification because we're putting base into the water. Large capacity, very exciting capacity, unknown effects. We're talking about engineering rock and distributing on a scale that's never been done before, and it could be quite extensive. This will all cost energy, water, and large amounts of material. I need just a little sip of water here for a second. Turns out talking for 3 hours is harder than I thought. Good. Okay, can we fertilize the ocean? So that's another way to imagine a decreasing carbon in the air. We put some minerals in the water, we grow algae, the algae take up CO2 and they die. And that's what's shown here. The oceans naturally absorb CO2. We add certain kinds of minerals, phytoplankton, which bloom, consume the CO2 and drop to the bottom. It's really a compelling idea. People like this idea because it's natural. Yeah, because we're just exploiting known algae. If you calculate the scales on which this could be done, at most we could drop down the atmospheric concentration of CO2 by 40 ppm. Enormous damage to local ecosystems. If you imagine going to a place, off the shore of India and now seeding that place with enormous quantities of minerals, which bloom these phytoplankton, any fish and other natural species in that area could be seriously damaged. So nobody really takes it seriously, but the real reason has to do with pumping gas, pumping fluid. If you look at these circulation patterns for CO2 in the near surface and what happens with dissolved organic carbon, this biological pump we refer to in these carbon cycles that has to do with the glace ages. And this pump is really only about 10 gigatons per year, and only a fraction of that is associated with the amount of carbon to sink, a fraction of which sinks deep enough really to go to be sequestered for centuries. And so if we're going to do this, then we also need to build a lot of pipes to move a lot of the water around so that we can get these degraded materials down to the ocean floor. And so this would be a massive global scale fertilization and piping problem in order to move these around. And at maximum, maybe some fraction, on the order of a gigaton per year, could be extracted from the atmosphere. And it's really hard to imagine accomplishing this. There was an initial flurry of activity in the United States to do this kind of processing, and it is now not taken very seriously. Here's another picture. I like this cartoon a lot because it lays on a simple diagram the costs and benefits of these various techniques. So on this axis here, you have the negative emissions, that is sequestering carbon out of the atmosphere. Here's the energy per year that's required to accomplish it versus the energy per year that's produced. It's a very nice paper on Nature Climate Change. It's worth looking at. And this particular color scale represents the land requirements. And then the size of these droplets represents the water requirements. So those of you, by the way, who went to my assessment talk that I gave to the combined community, I talked about the visual display of information as being a really important new tool for students. And then look at all the information that's available on this graph through the clever use of pictures. I like this very much. Here's BECS, okay? You see the land requirements are pretty severe, but we produce a lot of energy, and we have a very significant impact on mitigating CO2. And this is why BECS is so popular. Direct air capture, the land requirements are minimal, but the energy requirements are extreme. But we also have a very significant impact. The water requirements for direct air capture are not so great, but the water requirements for BECS is pretty extreme. And so you can examine various technologies on graphs like this, and it allows you to sort of assess the status of the technology that you may be researching as part of your research activities. So let's summarize the same Nature Climate Change article with a series of bar graphs that shows us how to compare all these various technologies. So here I have a bar graph. This is the atmosphere. Here's carbon underground. Here's carbon in the land, carbon in the ocean. And fossil fuel energy, as we consume it right now, takes carbon out of the geology and adds it to the atmosphere. That's where we're at right now. So we want to ask about bioenergy. So bioenergy takes carbon from the land and it emits it into the atmosphere. That is, we just burn wood to make fuel. If we do CCS, like Professor Reimer has been talking about, we take carbon out of the ground, we generate energy, but we put carbon back in the ground. And so ideally it's net carbon neutral. Here's bioenergy plus the so-called BECS. So let's follow this out. We take biomass from the land, never gets to the atmosphere, it's sequestered, and therefore we reduce, because the land took up carbon, we decrease the amount of CO2 in the atmosphere. Direct air capture, just take it out of the air and put it underground. Enhanced weathering, take it out of the air, put it underground. Afforestation, take it out of the atmosphere, put it in the land. Ocean fertilization, take it, put it into the ocean from the atmosphere. So these are the ways to sort of visualize how these work in terms of these models or bathtubs for carbon. And so now we have to look at all the requirements necessary to accomplish this. A lot of land, a lot of water. We need nutrients that are depleted in the case of growing things, or we need fertilizer in the case of growing algae. Albedo modifications actually are a benefit for BECCS. If you take a parking lot and replace it with a forest, it has net benefits for temperature change locally. There are costs. The energy requirements for all these are really quite extreme. So without renewable energy and cheap renewable energy, not many of them are feasible. We need considerable investment to both pilot them and deliver them. Those investments have to come from people who have money. And how do they get that money? It's unclear. We can't rely on Bill Gates to fund all this. And so as a matter of public policy, we have to decide where these investments are. There are a lot of social effects associated with these, in particular the engineering of the land and water around us, the security, energy security, and of course the security of the land around you. And when there's CO2, you have a farm and people are putting gigatons of CO2 underneath your farm. There's a security and sensitivity issue there, and of course a safety issue. So in summary, the negative emissions technologies will most likely be necessary if we're going to meet the Paris Agreement. Net carbon dioxide removal from the atmosphere involves land use changes. All of these technologies need to be evaluated in terms of their costs, in terms of weather, energy, land, and there might be unforeseen negative consequences. And the real goal of climate intervention, after all, is to reduce radiative forcing. That is, reduce this greenhouse effect for the planet Earth. So it is 4:27. So I either end now or I end in 10 or 15 minutes. 10 minutes. I love Professor Singh. Fine. I made a small mistake and closed a file that I should not have closed. So if you will give me just one moment, because I know this is coming from my 10 minutes. Okay, I deleted the file. So I'll just say a few words, and then I want to go through the summary with you. So you'll get a little of your time back. I apologize. So what is it Reimer and his students do in the lab exactly with regard to carbon capture and sequestration? Because I have not included in any of these presentations work that's specific to the students and postdocs who work in my lab. And so I mentioned direct air capture. And we've talked about amines. So one of the things my group has been involved in is building porous materials in which we append amines inside the porous materials. And so what you have then is this really nice benefit of the carbamate chemistry that goes with absorption. That is, CO2 reacts with an NH2 group to form a carbamate. But you don't have the water. This happens in a porous medium. So I've been working with my students for 2 or 3 years now on designing these porous materials to do this. And we discovered something really quite surprising, which is rather than chemically tether an amine inside of one of these porous materials, we actually just add the amine to the material as a liquid. And the amine sticks to the walls of the pores. And when it sticks to the walls of the pores, it moves. It's fluxional, as we say in chemistry. That is, these amine groups are moving. And they move in a very strange way. They move in a way in which the enthalpic forces, that is the energy it costs to move, and the entropic forces, that is the number of configurations available to the molecules that move, are in a delicate balance. And there's a place in the world where that delicate balance also occurs, and that's in enzyme chemistry, where you're placing an active site in a pocket that's dynamic. So we were surprised. It was completely accidental, I should say. We were surprised that when we did an adsorption isotherm on these porous materials with the amines aligned in them, that the isotherm was a perfect step function. That is to say, none was absorbed, and then poof, it all absorbed at once. It wasn't Langmuirian at all, which grows slowly and rises. And it wasn't one of these type 2 or type 3 or whatever. It was a step function. It's really very rare in adsorption science. And we had a difficult time figuring out what it was. And 28 authors later in a paper in Nature, we figured out that what's happening is that there's a chain reaction occurring. The first CO2 molecule comes in, and it sort of weakens this dynamic process, which allows all the others to react instantly. And so that was the first exciting part, was to figure out this chemistry and the role of the delicate balance of entropy and enthalpy in this motion, so that we got these step functions. Why are step functions important? Because if you're going to desorb and adsorb, so imagine this is a temperature scale here, and you have this adsorption isotherm. At this temperature, it's all absorbed. At this temperature, it's none. And that delta T is like 10 degrees C for these materials. So that means temperature swing adsorption doesn't have to heat the bed very much to get the CO2 off and on again. So that was really exciting to us. And then we recognized, of course, that where does the step function occur in temperature? So you can tune the structure of the porous material, and you can tune the type of amines, and you can move that step function up and down in temperature. So we were able to craft the material so that it was optimal for doing desorption from a packed bed. So those of you that know engineering know about desorption from packed beds. You have to have heat transfer and so forth. So we were able to get the whole desorption process to occur below 100 degrees C. So water, doesn't matter whether water was there or not. So the effect of water went away. And then in the same studies, we recognized, can we tune that step function so that it's at 400 ppm? And you know why 400 ppm is important. That's the concentration of CO2 in the air. So I can run a temperature swing on a material where I capture CO2 at 400 ppm, change the temperature by 20 degrees, pull it off, go back and forth and back and forth. And so that's why Nature published the paper, is because we were able to knock sort of all these things off at the same time by really exploiting the kind of chemistry and physics that occurs in enzymatic systems. So we got lucky with that one, to be sure, but that's the kind of thing my research group does. And so sort of engineering and designing these porous materials for carbon capture. So let's call our attention then, in closing, to the summary of our course. Yeah? So for direct air capture, you want absorption to occur at room temperature, 20C, 30C at the most, depending. And you want the desorption temperature to be less than 50C. So you
After that, it's like decreasing.
And that's it. You cycle between room temperature and 50C, and the CO2 comes on and off and on and off. We did all. So we started a company to deliver these materials. And somebody earlier on in the course was commenting about the cost, in terms of carbon cost, to make these organic materials. And it's not trivial, but then once you have a goal, then you can start engineering the reactors to produce the materials and drop the product. So the first time we did this, we were lucky to make 100 milligrams of this material to do the initial studies. But we're at the point now where we can produce 100 kilograms a day, so which is not enough to save the Earth. But it's certainly a big step forward from 1 gram, and that's just been in a matter of a few months. So what have we've looked at this in 3 parts. And first, I reviewed what I consider to be overwhelming scientific evidence that the atmosphere is changing, humans are the cause, and that there are consequences on virtually every level of the planet. In the second part, I introduced carbon capture as an effective scheme to mitigate the disposal of our waste in the atmosphere, and in particular examined 3 technologies for capturing carbon: adsorption, absorption, and membrane separations. And then finally, we looked at sort of the geology of carbon sequestration, the environmental risks, projects that are taking place to demonstrate that it can happen, and the various geoengineering schemes to decarbonize the atmosphere. So my conclusion for the students here is that the Earth needs your help to devise and implement schemes to decarbonize the atmosphere. And although there are many technical and policy challenges, the fundamental chemistry and physics and engineering of carbon capture and sequestration really pose no fundamental limitations on employing them in saving the planet. I want to thank you all for giving up a week of your time. Professor Singh is coming? Oh, yeah. So